Module 6, Lecture A, Text Pipelines. By the end of this lecture, you will be able to tokenize raw text into sequences of tokens suitable for neural models, build vocabularies and map tokens to integer indices, handling unknown and padding tokens, and create PyTorch datasets and data loaders that yield padded text batches and labels. Core text tokenization, word and subword choices. When preparing text for neural models, a major choice is how to break it into tokens. Using whole words as tokens is simple and works reasonably well for languages like English in stable domains such as news. However, in fast-changing domains like social media, this creates a huge vocabulary with many rare words. That sparsity makes it harder for models to learn useful patterns and increases computational cost during both training and inference, because the language is so diverse and creative. Subword tokenization is a method that breaks words into smaller, reusable pieces, striking a balance between character-level and word-level representations. Instead of treating related words as completely separate, it splits them into shared parts so the model can reuse common patterns. This is especially helpful for rare or new words, which can be represented as combinations of known subword units instead of being marked as unknown. Modern systems learn a subword vocabulary that keeps frequent words intact while decomposing less common ones, which keeps the vocabulary size manageable, improves coverage of different texts, and helps the model generalize better to new data. Choosing between word and subword tokenization depends on the language, the task, and system limits. For languages like Chinese or Japanese, where words are not separated by spaces, subword or character-based tokenization is usually required. In multilingual or mixed domain settings, subword methods help keep the vocabulary manageable and reduce unknown tokens, especially for names or mixed language text. Word-level tokens remain useful when simplicity and interpretability matter, such as in educational tools. Many systems therefore default to subword tokenization for robustness and efficiency, but it is important to balance these advantages against the more intuitive nature of word-based tokens. Python code, word and subword choices. This script demonstrates the difference between word tokenization and subword tokenization using simple, intuitive examples. Its goal is to build a clear understanding of how each method breaks text into units. As you run the cells, you can observe the printed outputs and directly compare how the same text is segmented under each approach. This helps you develop an intuitive feel for the behavior and results of word versus subword tokenization. In this part of the script, you would normally add any external installations, but for this program, none are needed. The code runs entirely with Python's built-in features, so it does not rely on extra libraries. This makes the script simpler to use and easier to run without managing additional dependencies. We begin by defining a short list of example sentences that will be used to demonstrate tokenization. These sentences include phrases such as unbelievable movie with unbelievable acting, believer in believable stories, and new product X is unbelievably cool. They are chosen because they contain different forms of the word believe, which helps us see how whole words and smaller subword units are broken apart during tokenization. This setup creates a clear basis for later comparing word-level and subword-level tokenization methods in the script. We begin by showing the raw text inputs so learners can clearly see the sentences we will work with. A simple header announces that these are the raw texts. Then we go through each sentence in the list and print it with a dash in front, creating a neat, organized view. This clear display of the original sentences prepares learners to understand how these texts will be tokenized in the next steps. This function takes a piece of text and breaks it into individual words for later analysis. It first trims any extra spaces at the beginning or end of the text. Then it splits the text wherever there is a space, assuming that spaces separate words. The result is a list of words that can be used for simple natural language processing tasks. We build a word vocabulary by starting with a special unknown token assigned to 0, which will represent any word not seen in our data. Then we go through each sentence in our text list and split it into individual words using a simple tokenizer. For each word, we check whether it is already in the vocabulary, and if not, we add it with a new integer based on the current size of the vocabulary. This process creates a mapping from words to unique integers so that we can convert text into a numerical form for later processing. We now display the word vocabulary, which is a dictionary that assigns each unique word in our example sentences a unique integer identifier. Seeing this mapping shows exactly how each word is converted into a numerical form. This numerical representation is essential because it allows the text to be processed by algorithms in natural language tasks. In other words, the vocabulary connects the original words to the numbers that models can work with. To demonstrate word-level tokenization, we take a sample sentence and first split it into separate words based on spaces. We then look up each word in a word vocabulary and replace it with its corresponding integer ID. If a word is not in the vocabulary, we assign it the special ID reserved for unknown words. The final result is a sequence of integer IDs that represents the original sentence at the word level. We display a short message to indicate that we are about to show the word tokens and their integer identifiers for a given example sentence. Then we pair each word with its corresponding integer using a function that combines the two sequences into tuples. Printing this list lets us see exactly how each word is mapped to a unique number in the vocabulary. This demonstrates the outcome of word tokenization and how the vocabulary is used to convert text into numerical form. This function breaks text into subword tokens based on a list of suffixes. It first splits the input into individual words. Then, for each word, it checks whether the word ends with any suffix that is shorter than the word itself. If a match is found, the word is split into a stem and that suffix, and both are added to the token list, with the suffix marked by an underscore. If no suffix matches, the whole word is added as a single token. The function returns the final list of tokens, which contains stems and their suffixes as separate elements. This section explains that we define a list of common subword endings, such as able, ably, and to break words into smaller parts. By detecting these suffixes, the system can split a word into its stem and its ending. This makes the tokenization process more flexible and better at handling different word forms. As a result, the subword tokenization becomes more accurate and adaptable. We build a subword vocabulary by starting with a special token for unknown words, which helps handle words not seen during training. Then, we process each sentence in our dataset using a subword tokenization function that splits words into smaller parts based on predefined suffixes. For every subword produced, we check whether it is already in the vocabulary, and if not, assign it the next available integer ID. In this way, we create a mapping from subword units to unique IDs, allowing text to be encoded at a more fine-grained linguistic level. We first print a short message to let the user know that the subword vocabulary is about to be shown. Then we display the subword vocabulary dictionary, which maps each subword token to a unique integer. This mapping reveals how the tokenizer has broken the original text into smaller pieces. Understanding this dictionary is important for seeing how the subword tokenizer interprets and processes input sentences. We begin by using a subword tokenizer to break the sentence into smaller units based on predefined suffixes. Then we look up each of these subword units in a subword vocabulary to find its corresponding integer identifier. This maps every token to a unique number, so the entire sentence can be represented in numerical form. That numerical representation is what we use for later processing or analysis. We begin by printing a short message to signal that we are about to show subword tokens and their integer identifiers, so the user knows what to expect. Next, we pair each subword token with its corresponding integer from the subword vocabulary, using a function that combines the two sequences. This produces a list of pairs, where each pair contains a subword and its numeric ID. Finally, we print this list to reveal how each subword token is mapped to a number, helping us understand how the tokenization process has converted the example sentence into numerical form. This script compares word tokenization with subword tokenization using simple sentences. It first builds a word vocabulary by splitting sentences on spaces, assigns each unique word an integer ID, and shows how a sentence is represented as a sequence of these word IDs. It then builds a subword vocabulary by splitting words into stems and common suffixes, such as able, ably, and and assigns IDs to these smaller units. The same sentence is tokenized again using these subword units, and the resulting tokens and IDs are displayed. Overall, the example shows how subword tokenization can break words into smaller, meaningful pieces and capture more detailed information than basic word-level tokenization. Text normalization basics. Before we tokenize text, we first normalize it to make the input more consistent for models. Natural language is unpredictable, with differences in capitalization and repeated characters. So normalization reduces these variations while keeping the meaning the same. For example, converting everything to lowercase lets the model treat apple and apple as identical, though this may not be appropriate when capitalization carries important information, such as recognizing names in news articles. Therefore, normalization choices must be tailored to the specific task, carefully deciding which details to keep and which to discard. When normalizing text, it is important to treat characters, accents, and writing systems consistently, especially when multiple languages are mixed. This often involves converting everything to a standard Unicode form so that visually identical characters are handled the same and do not cause tokenization errors. Depending on the task, you may choose to remove accents, such as treating cafe and cafe as equivalent to improve search recall, or keep them when they carry important meaning, as in language learning. It is also helpful to normalize whitespace by turning tabs and multiple spaces into a single space so token boundaries are easier to detect and formatting differences cause fewer problems. When normalizing text, we must decide how to handle numbers, symbols, and informal writing based on the task. In financial analysis, we usually keep exact values like percentages and dollar amounts, while in sentiment analysis, we might replace all numbers with a generic placeholder. For social media text, we often shorten elongated words and repeated punctuation, such as turning many repeated letters or exclamation marks into a single one. However, we should preserve meaningful differences, like distinguishing between a simple OK and a more intense OK with many exclamation points. Overall, the goal is to simplify the text while still keeping distinctions that matter for the specific application. Python code, text normalization basics. This script introduces basic text normalization by applying a few simple rules before tokenization. It shows how raw text is cleaned and standardized, so later processing becomes more reliable. As you run the cells, you can observe each transformation step by step, and see how the text changes at each stage. To install an external library like TensorFlow, you typically run a pip install command that specifies the exact version you need, such as version 2.20.0. Choosing a specific version helps keep your project compatible with its dependencies. It also reduces the risk of problems that can occur if a newer or older version is installed instead. We begin with a list of raw example sentences that contain deliberate formatting problems, such as extra spaces, too much punctuation, and stretched out words. This list serves as the starting point for applying various text normalization methods. By processing these messy sentences, we can see how each normalization step cleans and standardizes the text. The goal is to observe how the text becomes clearer and more consistent after each transformation. We begin by printing a simple header that labels the section as the original texts. Next, we go through each sentence in the list of raw texts and print it with a dash in front. This step shows every sentence in its untouched form. By doing this first, we create a clear baseline that we can later compare with the normalized or processed versions. We begin by importing the regular expressions module, which is used to search, match, and modify text based on patterns. In this script, it helps us clean and normalize text by detecting specific character sequences. For example, we can find and replace multiple spaces or repeated punctuation marks. This kind of cleanup prepares the text for later processing steps. This text describes a function that normalizes input text to make it easier to process. It first converts all characters to lowercase so the text is consistent. Then it uses a pattern matching approach to replace any run of white space with a single space, which removes irregular spacing. Finally, it trims spaces from the beginning and end of the text and returns this cleaned, normalized version. This function cleans up text by reducing excessive punctuation. It uses pattern matching to find any run of 3 or more exclamation marks and replaces it with a single exclamation mark. It does the same for 3 or more dots, turning them into a single period. By collapsing these repeated marks, the text becomes more readable and easier to handle in later processing steps. This function cleans up elongated words in text, such as when someone types a word with many repeated letters. It uses regular expressions to detect any sequence of 3 or more identical letters in a row. When it finds such a sequence, it shortens it to just 2 of that letter. This normalizes exaggerated spellings into a more standard form, making the text easier to process later. We create an empty list to hold the cleaned texts, then process each raw text in turn. For every text, we first compress any repeated punctuation marks using a dedicated function. We then shorten elongated words by reducing long runs of the same letter to just 2. After that, we convert the text to lowercase and standardize the spacing. Once all these steps are applied, we add the fully normalized text to our list. Next, we print the normalized texts so we can compare them with the originals. We begin by printing a clear header that says normalized texts to separate this output from earlier results. Then we go through each normalized text in the list and print it with a dash in front. This simple formatting makes it easier to see how the normalization process has cleaned and standardized each piece of text. We begin by printing a message to indicate that we are about to display tokens after normalization. For each normalized sentence, we split the text at spaces to create a simple set of tokens. This gives us a basic tokenization of the sentence into separate pieces. We then print the resulting list of tokens for each sentence, so we can see how the text has been divided into individual words or components. This script shows how to clean and standardize text using simple normalization steps. It starts by printing the original sentences, then compresses repeated punctuation and shortens elongated words. Next, it converts all text to lowercase and normalizes spaces to create a more uniform format. Finally, it splits each clean sentence into tokens based on spaces, illustrating how basic regular expressions can prepare text for further processing. Punctuation in tokenization. Punctuation plays an important role in text tokenization because it carries structure and subtle meaning that neural models can use. Marks like commas, question marks, and exclamation points signal pauses, boundaries, and emphasis. Tokenizers must decide whether to keep these marks separate, attach them to words, or remove them, and this choice changes what the model can learn. For example, treating a word with an exclamation point as different from the same word without it helps the model detect strong sentiment. In tasks such as sentiment analysis or dialogue modeling, preserving punctuation often improves performance by helping the model distinguish neutral from emotionally charged language. When handling punctuation in real-world text, inconsistent treatment of things like repeated symbols or creative spacing can cause problems, because every variation might become a separate token and make the vocabulary unnecessarily large. A better approach is to normalize these patterns while still keeping useful signals. For example, you can map repeated question marks to a single question mark token, or convert emoticons into standardized tokens that represent emotions. This strategy preserves important expressive cues while keeping the vocabulary manageable and improving model efficiency. Punctuation should be handled differently depending on the language, domain, and task, so there is no single rule that works everywhere. In formal texts like legal or academic writing, keeping commas, quotation marks, and similar symbols helps models capture structure and who said what. For simpler tasks, such as pulling keywords from product titles, much of the punctuation can be removed without losing important meaning. However, domain-specific symbols like hashtags or web addresses should be kept as special tokens because they carry key information. Overall, when designing a tokenization strategy, you must balance how punctuation supports expressive detail with how it affects model efficiency. Python code, punctuation in tokenization. This script examines how punctuation is handled during tokenization and shows how different rules can change the resulting sequence of tokens. It demonstrates the impact of these rules on the output and helps you see how token boundaries shift when punctuation is treated in different ways. You can use it to compare a simple tokenizer with a custom tokenizer and better understand how their behavior differs. This script mentions that you might sometimes need to install a separate regular expression library when using external packages. But in this case, that is not necessary. The code here uses only Python's built-in standard library features. As a result, everything you need for regular expressions is already included with Python by default, and no extra installation is required. The script uses the regular expressions module to support custom tokenization. Regular expressions allow it to define complex rules for how text is split into tokens, going beyond simple splitting on spaces. This makes it possible to control how punctuation and special characters are handled. As a result, the script can perform more precise and nuanced text analysis. We begin with a small set of short text examples that contain expressive punctuation, such as question marks, exclamation marks, and a smiley face emoticon. One example shows surprise with a question followed by an exclamation. Another uses repeated question and exclamation marks to stress excitement or disbelief. And a third adds a smiley to create a friendly tone. These texts are collected to illustrate how different punctuation styles influence tokenization, and to serve as a basis for comparing tokenization methods later in the script. The script begins by printing a header that labels the upcoming output as raw texts. It then loops through each entry in a list of texts and prints each one on its own line, preceded by a dash. This creates a simple, readable list of the original sentences. Showing these unprocessed texts first makes it easy to compare them later with their tokenized versions produced by the rest of the script. We define a simple function called whitespace tokenize that takes a text string and breaks it into words. Inside the function, it uses the split method on the text, which separates the string wherever there's a space. This produces a list of tokens, where each token is one word from the original text, because it relies only on spaces to separate words. This is a very basic form of tokenization. We use a regular expression pattern to break text into tokens by separating punctuation from words. It groups together letters and digits as word tokens, and also treats certain punctuation marks like colons, semicolons, and parentheses as their own tokens. It further groups runs of exclamation points, question marks, or periods, and captures any other non-word, non-space character as a separate token. This method lets us split text into meaningful pieces while keeping punctuation distinct from the words. The regex tokenize function takes a piece of text and uses a regular expression pattern to break it into meaningful parts. It finds sequences of word characters, emoticons, and punctuation marks such as exclamation points and question marks. The function then returns these matched pieces as a list of tokens. This method provides more precise tokenization than simply splitting on spaces, because it keeps punctuation and emoticons as separate recognizable tokens. This function processes a list of tokens to normalize punctuation and emoticons. It scans each token and replaces any sequence of multiple question marks with a single question mark, and any sequence of multiple exclamation marks with a single exclamation mark. If a token is a smiley or frowny face emoticon, it is replaced with the word emoticon. All other tokens are left unchanged, and the function returns the new list of normalized tokens. The code first prints a short header to introduce a comparison of tokenization methods. It explains that the comparison will only use the first two texts from the list. This lets the listener know that the detailed results that follow are based on a small, focused subset of the data. Limiting the scope in this way keeps the output clearer and easier to interpret. We process only the first two texts in our list to keep the demonstration simple. For each text, we first tokenize it by splitting on spaces. Then, use a more advanced regular expression tokenizer that separates punctuation from words and captures items like words, emoticons, and punctuation marks. We then normalize the tokens by collapsing repeated question and exclamation marks into a single mark and replacing emoticons with a placeholder. Finally, we compare the outputs to show how these different tokenization and normalization steps change the way the text is broken into tokens. This script compares two ways of handling punctuation during tokenization. It first uses a simple whitespace approach that splits text only on spaces, so punctuation remains attached to words. It then applies a regular expression-based tokenizer that separates punctuation from words, producing more detailed tokens. The script also normalizes these tokens by collapsing repeated question and exclamation marks into a single mark and replacing emoticons with a placeholder. Running the code lets you see how these different methods change the resulting token sequences. Vocabulary and indices. Frequency-based vocabulary. When building a vocabulary for text models, you choose which tokens from your data get their own indices based mainly on how often they appear. You count token frequencies, sort them, and prioritize common words and important domain terms because they give the model enough examples to learn stable representations. Very rare tokens appear too few times to be statistically useful and are expensive to model individually. By focusing on frequent tokens and ignoring most rare ones, you capture the most useful parts of the language for the model to learn. When building a frequency-based vocabulary, you usually limit its size, either by keeping only the most frequent tokens or by requiring each token to appear a minimum number of times. A larger vocabulary can capture more detail in the data, but uses more memory and can slow training. A smaller vocabulary is faster and more efficient, but may lose important nuances. Choosing the right size is a trade-off that depends on your dataset, the complexity of your task, and your available computing resources. Frequency-based vocabularies are useful because they adapt to the specific data you are modeling, such as slang and emojis in social media or technical terms in legal documents. By prioritizing tokens that appear most often, the model can handle common language more efficiently during training and inference. At the same time, you should deliberately include rare but important tokens, like specific drug names, even if they do not occur frequently. Overall, this strategy provides a strong baseline for choosing tokens while leaving room to adjust based on domain knowledge and the needs of the task. Python code, frequency-based vocabulary. This script shows how to build a vocabulary based on how often words appear. It starts with a small text corpus, counts how frequently each token occurs, and then assigns each token a numerical index. The process also includes special handling for certain tokens, such as reserved or uncommon items, so the final mapping from tokens to indices is both systematic and practical for later use. To use external libraries in your script, you need to install them first, such as installing TensorFlow version 2.20.0. Doing this makes sure all required dependencies are available. It is especially important when your code depends on specific features or compatibility provided by that exact version of TensorFlow. Without the correct version installed, the script may not run properly. We begin with a small set of short sentences called our corpus, which forms the basic data for vocabulary analysis. Each sentence is a simple text example that we will use to show how to count word frequencies and construct a vocabulary. The sentences focus on deep learning and natural language processing, giving our demonstration a relevant context for these topics. This function tokenizes text by turning it into a uniform list of words. It first converts all characters to lowercase so that words with different capitalization are treated the same. Next, it trims any extra spaces at the beginning or end of the text. Finally, it splits the cleaned lowercase text into separate words based on spaces, producing a simple list of tokens suitable for basic text processing. We process each sentence in the corpus by passing it through a simple tokenize function that splits the sentence into individual words, or tokens. This produces a list of sentences where each sentence is now represented as a list of its component words. Creating this tokenized representation is an essential preparation step that allows us to perform later operations, such as counting word frequencies or mapping words to numerical indices. We begin by displaying the tokenized corpus so we can clearly see the data we are working with. By printing the list of tokenized sentences, we check that the original text has been correctly split into individual tokens. This verification step is important because it confirms that the text has been processed as intended. Understanding this structure gives us confidence before moving on to more advanced analysis or processing steps. We build a frequency dictionary by starting with an empty structure to store how often each token appears. Then we go through every list of tokens in the corpus, and examine each token one by one. For each token, if it is already in the dictionary, we increase its count. If it is not, we add it with a count of 1. After processing the entire corpus, the dictionary maps each token to the number of times it occurs. We first print a short message to indicate that we are about to show the token frequencies. Then we display the frequency dictionary itself, which lists how often each token appears in the corpus. This allows us to quickly inspect the counts and confirm they look correct. Verifying these frequencies at this stage helps ensure the data is accurate before we move on to later processing steps. We build the vocabulary by sorting tokens so that the most frequent ones come first. When 2 tokens have the same frequency, we break the tie by ordering them alphabetically. This is implemented with a sorting rule that prioritizes higher frequency and then the token's text. As a result, the vocabulary is ordered by frequency while remaining stable and consistent whenever there are ties. In our vocabulary, we use 2 special tokens to handle tom and edge cases. A padding token is used to fill in empty positions so that all sequences have the same length. An unknown token is used whenever a word does not appear in our vocabulary. Together, these tokens let us manage variable length inputs and out-of-vocabulary words in a consistent way. We limit our vocabulary size, including special tokens, to 8. This means there can be at most 8 different tokens, counting any special ones such as padding or unknown tokens. Setting this upper bound reduces how many tokens the model must store and process. As a result, it helps control memory use and improves computational efficiency. We start by creating a vocabulary list that includes 2 special tokens. One token is used for padding, so that all input sequences can be adjusted to the same length. The other token represents any unknown word that does not appear in our vocabulary. These 2 tokens are essential for handling variable sequence lengths and out-of-vocabulary words in a consistent way. We build the vocabulary by adding tokens in order of how often they appear, stopping when we reach the maximum allowed size. For each token in the sorted list, we first check whether the vocabulary has already hit this limit. If it has, we stop adding new tokens. If not, we include the current token. This way, only the most frequent tokens are kept, making the vocabulary compact and efficient. We build a mapping from each token to an integer index using a dictionary that pairs every token with its position in the vocabulary list. By enumerating the vocabulary, we obtain both the index and the token, then store the token as the key and its index as the value. This mapping lets us quickly convert tokens into numerical form, which is crucial for many machine learning models that operate on numbers rather than raw text. We build a reverse mapping from indices back to tokens by flipping the original token to index dictionary. For each token and its index, we create a new entry where the index becomes the key and the token becomes the value. This new dictionary lets us quickly convert numerical indices back into their original token forms. Having this reverse lookup is important for interpreting model outputs and for debugging tokenization behavior. Next, we print out the final vocabulary tokens to see which words were included in our vocabulary list. This step lets us confirm that the selection process worked as intended and gives us a clear view of the resulting vocabulary size. The output shows both the special tokens and the most frequent words that were extracted from our text corpus. We now look at the mapping from tokens to their integer indices, which is stored in a dictionary called token to index. By printing this dictionary, we can see how each token in the vocabulary is paired with a unique number. This mapping is essential because it converts text into numerical form. Once in numerical form, the data can be processed by machine learning models that operate on numbers rather than raw text. This function converts a list of tokens into a list of numeric indices using a given mapping from tokens to indices and a special index for unknown tokens. For each token, it checks whether the token appears in the mapping. If it does, the function uses the mapped index. If it does not, the function substitutes the index assigned to the unknown token. In this way, every token is converted to a valid index, even when the token is not part of the known vocabulary. We convert each tokenized sentence into a sequence of numerical indices. For every list of tokens in the corpus, we apply a mapping that replaces each token with its corresponding index. This mapping is based on a predefined dictionary from tokens to indices. And if a token is missing, we use the index reserved for unknown tokens. As a result, our text is transformed into numerical form, ready for further processing or modeling. We label the next part of the output with the phrase indexed corpus, then show the contents of the indexed corpus variable. This variable holds the integer versions of the tokenized sentences. By examining this output, we can check how each token in the text has been converted to its corresponding index in the vocabulary. This step helps verify that the token-to-index mapping is working as intended. This script builds a small, frequency-based vocabulary from a set of sentences. It first converts each sentence into lowercase word tokens and counts how often each word appears in the entire collection. Based on these counts, it sorts the tokens by frequency and creates a vocabulary of limited size that includes special entries for padding and unknown words. Each word in the vocabulary is then mapped to an index so that sentences can be represented as sequences of integers. This process is a common way to prepare text data for machine learning models in natural language processing. Special UNK and PAD. When we convert text into tokens with integer indices, a key issue is how to handle words that are not in the vocabulary. To solve this, we reserve a special unknown token, often called UNK, and map every out-of-vocabulary word to this single index. This prevents the system from failing and clearly signals to the model that an unrecognized token is present. By always including this reserved UNK entry in the vocabulary, any missing token can automatically default to it, keeping the process simple and consistent. The padding token, or PAD, is used in neural models to handle text sequences of different lengths by extending shorter sequences so they match the longest one in a batch. These PAD tokens are just placeholders, not real words, and tell the model which positions to ignore during processing. PAD must have its own index in the vocabulary, and parts of the model such as the loss function and attention mechanism must treat this index as non-informative, so the model does not learn from these artificial tokens. Assigning fixed indices to special tokens like padding and unknown is important for consistent text processing. For example, using 0 for padding and 1 for unknown ensures that all parts of the system recognize them in the same way. This makes tasks like masking and computing sequence lengths easier and more reliable. It also helps models handle unexpected language and different text lengths, which supports robust performance in applications such as translation and sentiment analysis. Treating these tokens as standard parts of the vocabulary keeps the mapping from human language to numerical representations stable for neural networks. Python code, special UNK and PAD. This script introduces the special UNK and PAD tokens used in text processing. It builds a very small vocabulary that includes these tokens, then demonstrates how words from a sentence are mapped to numerical indices. By doing this, It shows how raw text is converted into the integer sequences that machine learning models expect as input. The commented line about installing TensorFlow is a placeholder for a command that would add the TensorFlow library using a package manager such as pip. It suggests that TensorFlow may be required to run or extend the script, even though the current version of the script does not actually use it. Including this line signals a possible future dependency, especially if the script is later integrated with machine learning models or expanded with additional features. We will work with a tiny corpus made of 3 short sentences. I love PyTorch, PyTorch loves NLP, and I enjoy deep learning. This small set of sentences will be our sample data for building a vocabulary. Using it, we can show how text is broken into tokens and then converted into numerical indices. These indices are what machine learning models actually use when processing language. We define 2 special tokens to help process text. A padding token is used to fill sequences so they all have the same length. An unknown token is used to stand in for any word that is not in the vocabulary. This way, every word in a sentence, even unfamiliar ones, can still be mapped to an index that the model can handle. In many natural language processing tasks, we assign fixed indices to special tokens to keep sequences consistent. The padding token, used to extend sequences to the same length, is given index 0, so it has a standard place in the vocabulary. The unknown token, which stands for any word not in the vocabulary, is assigned index 1. This setup lets models handle missing or unseen words while keeping input sequences uniform during training and inference. To build a word frequency dictionary, we start with an empty dictionary and process each sentence in the corpus. We split each sentence into words. Then for every word, we either add it to the dictionary with a count of 1 or increase its existing count by 1. Repeating this for all sentences produces a dictionary that records how many times each word appears in the corpus. We set the minimum frequency for including a word in our vocabulary to 1, meaning any word that appears at least once in the corpus is kept. This threshold filters out only words that never appear, while still capturing every word present in our small dataset. As a result, the vocabulary stays manageable, but remains complete for the data we are using. We start building the vocabulary by adding 2 special tokens, one for padding and one for unknown words. These are always assigned the first 2 indices, with padding at 0 and unknown at 1, so their positions are fixed and predictable. This consistency is important in natural language processing because it helps us handle missing words and pad sequences to the same length. With these tokens in place from the beginning, managing variable length text inputs becomes much simpler and more reliable. We now expand the vocabulary by adding words from the word frequency dictionary. For each word, we first check that its frequency meets the minimum threshold and that it is not already in the vocabulary. If it passes both checks, we assign it a new index based on the current size of the vocabulary, effectively placing it at the end. This way, every word that appears often enough in the corpus receives a unique index, extending the vocabulary beyond the initial special tokens. This line builds a reverse lookup from indices back to tokens using a dictionary comprehension. It goes through each token and its index in the vocabulary and flips them, so the index becomes the key and the token becomes the value. With this reverse mapping, you can quickly find which token corresponds to a given index. This is important for turning model outputs, which are usually indices, back into human-readable text. This function converts a list of tokens into a list of numerical indices using a given vocabulary. It takes the token list, a vocabulary dictionary, and a special index for unknown tokens. For each token, it looks up the token in the vocabulary and adds the corresponding index to the result. If a token is not in the vocabulary, it adds the unknown token index instead. The function then returns the full list of indices, providing a numerical representation of the original tokens based on the vocabulary. We define a function that ensures a sequence of indices has a fixed length. If the sequence is longer than the allowed maximum, we cut it off at that maximum length and return the truncated version. If it is shorter, we compute how many extra positions are needed and pad the sequence by adding that many padding tokens at the end. These padding tokens all use a specified padding index, so the final output always has the same fixed length. We begin by creating a few example sentences to test how the model handles words that may not be in its vocabulary. The first sentence, "I love PyTorch," uses only familiar words. The second, "PyTorch loves transformers," adds the likely unknown word transformers. And the third, "Deep learning rocks," adds another possible unknown word, rocks. Using these sentences, we can observe how the model converts text into sequences of indices and how it uses special tokens to represent words that are not in its vocabulary. We begin by taking each example sentence and breaking it into individual words, forming a list of tokens. This step, called tokenization, converts a sentence from a single string of text into an ordered sequence of words. Once tokenized, these word sequences can be processed further, such as by mapping each word to a numerical index. This numerical form is what we ultimately feed into our model as input. We convert each sentence into a sequence of numerical indices by mapping every token to its position in the vocabulary. A mapping function looks up each token and replaces it with its corresponding index. If a token is not in the vocabulary, it is replaced with the index reserved for unknown tokens. This way, every word in our examples is represented as a number, which is necessary for inputting the data into machine learning models. To choose the maximum length for padding sequences, we first measure how long each sequence is in our list of example indices. We then use a function to find the single longest sequence among them. That longest length becomes our maximum length. We use this value to pad all other sequences so they match it, giving the model uniform input sizes. We pad each sequence of indices so they all share the same length. To do this, we go through each sequence in the list and pass it to a padding function along with the maximum desired length and a special pad index. If a sequence is longer than the maximum length, the function cuts it off, and if it is shorter, the function adds pad tokens at the end. This process ensures that every sequence ends up with a uniform length, which is important for later processing. The code prints the vocabulary dictionary, which lists both special tokens and regular words with their assigned indices. This output lets you check that the vocabulary was built correctly and that each token has a unique position. Such a mapping from tokens to indices is essential for turning text into numerical data that machine learning models can understand and process. We now loop through each word and its corresponding index, using a function that lets us walk through both lists at the same time. For every pair, we print the original words from the example sentences next to their index sequences. This lets us check how each word is converted into its numerical form based on the vocabulary we created earlier. It clearly shows how both known and unknown words are handled in the transformation from text to indices that a model can process. The code prints the final padded batch of indices, showing how each sequence has been extended or trimmed to a uniform length using a padding token. This display makes it clear where padding has been added to shorter sequences. Seeing these padded sequences helps you understand how the model will handle input data that originally had different lengths. This script shows how to handle special tokens like unknown and padding when preparing text for machine learning models. It builds a small vocabulary from a set of sentences. assigns fixed indices to the padding and unknown tokens, and maps each word to an index based on how often it appears. Example sentences are then converted into sequences of these indices, using the unknown index for any word not found in the vocabulary. Finally, all sequences are padded to the same length with the padding index, demonstrating how raw text is turned into uniform numerical input for a model. Indexing token sequences. After you build your vocabulary and mapping from tokens to indices, you convert each sequence of tokens into a sequence of integers. This means every token in the text is replaced by its assigned number in the vocabulary, so the data can be processed as numerical tensors by neural models. It is crucial that this mapping is consistent and repeatable, so the same token sequence always produces the same index sequence. This consistency is important throughout training and deployment because it keeps the model's interpretation of language stable over time. When converting text into token sequences, it is important to assign a reserved index for any token that is not in the vocabulary so the model stays consistent. You must also insert special tokens that mark the start and end of sequences or separate different text segments. These design choices keep the model's input dimensions fixed, avoid mismatched mappings between runs, and help the model learn how different parts of the text relate to each other. When working with token sequences, it is essential to keep the original text, its tokenized version, and the indexed representation perfectly aligned, especially when labels are involved. In some tasks, like sentiment analysis, one label applies to the whole sequence, while in others, such as named entity recognition, each token has its own label. You must ensure that these labels stay synchronized with the token indices, even when unknown or special tokens appear. This careful alignment allows the model to learn correct patterns and produce outputs that can be accurately mapped back to the original text. Python code. Indexing token sequences. This script shows how to index sequences of tokens by mapping them to a vocabulary and handling special tokens. It demonstrates how each token is converted into an index based on a predefined mapping. The focus is on understanding how vocabulary mapping works and how special tokens are treated in this process. You are encouraged to run each part to observe the printed outputs and see how the indexing behaves in practice. This line is a comment explaining that, in Google Colab, you may need to install TensorFlow version 2.20 for the code to work correctly. The installation command is present but commented out, so it will not run automatically. To actually install TensorFlow in an environment where it is not already available, you would need to remove the comment symbol so the command can execute. We begin with a small set of short sentences called our corpus, made up of the phrases "great movie," "really great acting," and "bad movie, but great music." This simple corpus provides the basic data we need to build a vocabulary and explore how token indexing works. By using just a few sentences, it becomes easier to show how each word can be mapped to an index and how special tokens are handled in a clear, controlled setting. In working with text sequences, we use special tokens to keep everything consistent. A padding token fills out sequences so they all have the same length. An unknown token stands in for any word that is not in the vocabulary. A beginning of sequence token marks where a sequence starts, and an end of sequence token marks where it finishes. Together, these tokens make it easier to manage sequences of different lengths and handle words the system does not recognize. We begin by creating an empty list that will store every word from all the sentences in our corpus. Then we go through each sentence, split it into individual words, and collect these words as tokens. Each set of tokens is added to the main list so that, in the end, we have one combined list containing every word from every sentence. This combined list is the basis for building a vocabulary of all unique words in the corpus. To build a consistent vocabulary from a corpus, we first collect all tokens and convert them into a set so any duplicates are removed. We then sort this set to produce a list of unique tokens in a fixed, predictable order. This deterministic ordering is important because it ensures that each token is always mapped to the same index, keeping the token-to-index mapping stable and consistent across runs. We start building our vocabulary by adding special tokens that handle key cases in natural language processing. A padding token is used to extend all sequences to the same length, and an unknown token stands in for any word that is not in the vocabulary. We also include a beginning of sequence token to mark where a sentence starts, and an end of sequence token to mark where it finishes. By defining these special tokens first, we make sure the vocabulary can properly represent these essential situations before we add the regular words from the text data. We now expand our vocabulary by adding all unique tokens found in the corpus. This step makes sure every distinct word in the sentences is included in the vocabulary. As a result, each word can later be mapped to a specific index. By doing this, we prepare the vocabulary to handle any token in the corpus and convert sentences into sequences of indices. We build a mapping from each token to an integer index using a dictionary. By enumerating over the vocabulary list, we get each token along with its position. For every token, we store its position as the value and the token as the key. This creates a structure that lets us quickly look up the index of any token in the vocabulary. We build a reverse mapping from indices back to tokens by flipping the original token-to-index dictionary. For each token and its index, we create a new entry where the index becomes the key and the token becomes the value. This reverse dictionary lets us turn sequences of indices back into their original tokens. As a result, we can easily reconstruct sentences or other text from index data. We begin by printing all the vocabulary tokens, including both special tokens and those learned from the corpus, to see exactly which tokens the model can recognize. We then display the mapping from each token to its numerical index. This mapping is essential because it allows us to convert text tokens into numbers that a machine learning model can process. By examining both the tokens and their indices, we gain a clear understanding of how the text is represented in numerical form for further computation. This function converts a list of tokens into their numerical indices using a given mapping. It creates an empty list of indices, then goes through each token in the input. For each token, it looks up the corresponding index in the mapping and adds it to the list. If a token is not found in the mapping, it adds the index reserved for unknown tokens instead. In the end, it returns the full list of indices, providing a numerical representation of the original token sequence. This function adds special boundary tokens to a sequence of tokens. It takes a list of tokens along with one token that marks the beginning and another that marks the end. It returns a new list where the beginning marker comes first, then all the original tokens, and finally the end marker. This helps clearly indicate where a sequence starts and ends, which is important in many natural language processing tasks. We begin by choosing a sample sentence from our corpus, in this case, the second sentence in the list. We then split this sentence into individual words to create a sequence of tokens. This tokenized form prepares the sentence for later steps, such as adding special boundary markers or converting the words into a sequence of numerical indices for further processing. To prepare a sentence for further processing, we first add special boundary tokens to its list of tokens. A helper function is used to place a beginning of sequence token at the start and an end of sequence token at the end. This function takes the original tokens and the chosen boundary markers as input, and returns a new list that includes them. Clearly marking where the sequence starts and ends is essential for later stages of the processing pipeline. We use a helper function to turn a list of tokens, including boundary markers, into a sequence of numerical indices. The function takes the token list, a mapping from each token to its index, and a special token that represents unknown words. As it goes through each token, it looks up the token in the mapping and adds the corresponding index to the result. If a token is not found, it instead adds the index of the unknown token. This produces a numerical representation of the token sequence that can be used for later processing or analysis. We start by printing the original tokens from the example sentence, which are simply the individual words split from the text. Then we show these tokens again, but this time with special markers added at the beginning and end to indicate the sequence boundaries. Finally, we display the sequence of numerical indices that correspond to each token in the vocabulary. This illustrates how text is transformed into indexed form, a key step in many natural language processing tasks. We introduce a new sentence, great soundtrack, that is not part of the original corpus, and break it into individual word tokens. This example is used to show how the system processes tokens that do not appear in its predefined vocabulary. In particular, it highlights how unknown tokens are detected and handled by the code. We begin by adding special boundary tokens to the list of new tokens using a helper function that places them at the start and end of the sequence. This means we insert a beginning of sequence token at the front and an end of sequence token at the back. Doing this clearly marks where the sequence starts and ends, and prepares the tokens for any further processing steps. We use a helper function to convert a list of new tokens, including boundary markers, into their corresponding numerical indices based on a predefined mapping. For each token, the function looks up its index in the mapping and replaces the token with that index. If a token is not found in the mapping, the function uses the index assigned to the unknown token instead. This way, every token in the list is turned into a valid numerical representation, even when it is not part of the known vocabulary. We first show the new tokens, which are the words from the sentence split into a list. Then we display these tokens again with special markers added at the beginning and end to indicate sentence boundaries. Finally, we present the sequence of numerical indices that correspond to each token in the vocabulary, including the index used whenever a token is not recognized and must be treated as unknown. We reconstruct the original tokens by going through each index in the new index sequence and using the index-to-token mapping to look up the matching token. This round trip from tokens to indices and back must be consistent and deterministic, so that the same indices always produce the same tokens. After reconstruction, we print the tokens to confirm that the sequence matches the expected result, which shows that the mapping and conversion steps are functioning correctly. This script shows how to convert sentences into sequences of token indices for use in machine learning. It builds a vocabulary from a small corpus, including special tokens for padding, unknown words, and sentence boundaries, and assigns each token a unique integer index with a reverse mapping back to tokens. The script then processes example sentences by adding boundary tokens, converting them to index sequences, and printing the numerical representation. It also demonstrates how words not in the vocabulary are mapped to a special unknown index, and verifies that the original tokens can be reconstructed from the indices, ensuring a consistent and reversible encoding of text. Padded text batching, handling variable lengths. When working with text data, a major issue is that inputs can have very different lengths, from short snippets to long documents. Neural networks, however, expect each batch of inputs to have the same shape so they can be processed efficiently. To handle this, you need a data pipeline that converts variable-length texts into uniform batches, avoiding errors and wasted computation. Understanding this requirement is essential before you decide how to pad or truncate sequences in your training loop. In sentiment analysis, text inputs can have very different lengths, such as a short comment versus a long review. After converting these texts into sequences of token indices, their lengths will not match, so they cannot be directly stacked into a single tensor. Because neural networks require inputs with consistent shapes, the data pipeline must adjust these variable length sequences into batches that share a common length dimension. This allows the model to process all examples efficiently while preserving the original information as much as possible. How you handle variable sequence lengths has a direct impact on model performance, memory use, and fairness. Padding everything to the longest sequence can waste resources and slow training, especially with very long inputs, while aggressive truncation can remove important context. A better approach is to use a smart batching strategy, such as grouping examples with similar lengths or setting limits tailored to the task. This keeps the data pipeline efficient while respecting both the nature of language data and the constraints of the model. Padding and attention masks. When we pad text sequences to make them the same length, we add special tokens that are not real input. These padding tokens let us batch data efficiently, but they can mislead the model if it treats them like normal tokens. This is especially problematic for attention mechanisms in transformers, which combine information from all positions in a sequence. To prevent the model from focusing on padding, we use attention masks that mark which tokens are valid, so the model concentrates only on the actual content. An attention mask tells the model which parts of a padded sequence are real data and which parts are just padding. When sequences, like emails, are padded to the same length, the mask marks the actual words and hides the padding. This way, during attention calculations, the model focuses only on meaningful content. As a result, padding does not interfere with the attention scores or distract the model from the real information. Attention masks are essential in transformer models because they prevent the model from treating padding tokens as real data. Without masks, padding can distort attention patterns, create noisy gradients, and make training unstable. By masking out padding, the model focuses only on actual tokens, which improves its predictions and preserves the quality of learned representations. This is important not only for classification tasks, but also for translation, summarization, and other applications that mix short and long text inputs. Overall, attention masks help maintain both computational efficiency and reliable model behavior. Python code, padding and attention masks. This script demonstrates how padding and attention masks work using very small example sentences, so the ideas are easy to see. It is designed to be run as a complete sequence of cells in Google Colab. By following the script, you can observe how padding is applied to make sequences the same length, and how attention masks indicate which parts of the input should be considered by the model. A line that starts with an exclamation mark is used as a command to install a specific version of TensorFlow. In this case, version 2.20.0. This is common in environments like Google Colab. It makes sure that the exact required version of the library is available, so the code runs correctly. By fixing the version, it helps maintain compatibility and prevents problems caused by differences between TensorFlow versions. We start by importing the random library so we can generate random numbers in a controlled way. We also import the numerical computing library NumPy, which we will rely on to work with arrays and carry out mathematical operations efficiently throughout the script. Together, these tools provide the basic functionality needed for handling randomness and fast numerical calculations in our program. We start by importing TensorFlow, a widely used library for machine learning and deep learning. After that, we print the TensorFlow version currently in use. Knowing the exact version helps ensure that our code is compatible with other components and makes it easier to debug issues, since different versions can behave differently or offer different features. We begin by setting fixed random seeds in both the random and NumPy libraries so that any random operations give the same results every time the code is run. This practice is important for reproducibility because it lets us repeat experiments and get consistent outcomes. By using the same seed value in both libraries, we keep their random number generation aligned and make our results easier to compare. We begin with a few short example sentences, such as I love PyTorch, PyTorch loves NLP, and I love NLP, to demonstrate how padding and attention masks work in a neural network. This tiny set of sentences forms a simple corpus that lets us focus on the mechanics rather than complex language. From this corpus, we build a vocabulary and convert each sentence into a sequence of numbers. These numerical sequences are the form that text must take to be processed by machine learning models. We begin by building a simple dictionary that maps each word to a numerical index, and we include special entries for padding and for unknown words. The padding token is given index 0, and the unknown token is given index 1. Using these reserved indices lets us handle text sequences of different lengths and words that do not appear in our vocabulary in a consistent way during processing. We build a vocabulary by going through each sentence and splitting it into words. For every word, we check whether it is already in our vocabulary dictionary. If it is not, we add it and assign it a new index based on the current size of the vocabulary, so each word gets a unique identifier. This creates a mapping from words to indices, which we can later use to encode sentences as numerical sequences. The code prints the vocabulary mapping, which is the current dictionary that assigns each word in the corpus a unique index. This output lets you check that the vocabulary has been built correctly. It confirms that all words from the sentences are included, along with special tokens for padding and unknown words. We create an empty list to hold the encoded versions of our sentences, then process each sentence one by one. For each sentence, we split it into words and look up each word's index in the vocabulary dictionary. If a word is not in the vocabulary, we use the index assigned to the unknown token instead. The resulting list of indices represents that sentence, and we add it to our main list. In this way, every sentence is converted into a sequence of numbers based on the vocabulary mapping. The code first prints the encoded sequences before any padding is applied. This shows how each sentence in the toy corpus has been converted into a sequence of indices using the vocabulary mapping. By examining these sequences, we can confirm that every word has been correctly mapped to its index. This verification is important because it ensures the data is accurate before moving on to later steps such as padding and creating attention masks. We first need to find the longest encoded sentence, so we know how much to pad all sequences. To do this, we go through each encoded sequence, measure its length, and then use a function that returns the maximum of these lengths. The result is the length of the longest sequence. We then print this maximum length, so it can be used later to pad every sequence to the same size. We prepare our encoded data by creating two empty lists, one for padded sequences and one for attention masks. For each sequence, We determine how many padding tokens are needed to reach the maximum length and append that many padding tokens to the end. At the same time, we build an attention mask that marks each real token with a 1 and each padding token with a 0. These padded sequences and their corresponding masks are then stored in their lists for later processing. The code converts the padded sequences and attention masks from lists into NumPy arrays so they can be stored and processed more efficiently. It sets their data type to 32-bit integers to ensure they work correctly with later TensorFlow operations. This step prepares the data to be turned into TensorFlow tensors, enabling further manipulation and computation in the neural network workflow. Before creating TensorFlow tensors, the code verifies that the padded sequences and their attention masks have exactly the same shape. This check ensures that each element in a sequence has a matching mask value, which is essential for applying the attention mechanism correctly. If the shapes do not match, it signals a problem in data preparation that could cause errors in later computations. We first convert the padded sequences from a NumPy array into a TensorFlow constant using 32-bit integers so they can be processed by TensorFlow operations. We then do the same for the attention masks, but store them as 32-bit floats. This ensures both the sequences and their attention masks are in compatible TensorFlow tensor formats, ready for use in later computations. The code first displays the padded input sequences by converting the TensorFlow tensor to a NumPy array, so you can see how all sequences have been extended to the same length. It then does the same for the attention masks, showing which positions in each sequence contain real data and which are just padding. These masks guide the model during training or inference, so it focuses on the meaningful parts of each sequence and ignores the padding. We create a small embedding layer where each word is represented by a vector of 4 numbers. Using the Keras embedding layer in TensorFlow, we set the input dimension to the vocabulary size so the layer knows how many unique words to handle. We set the output dimension to 4 to define the embedding size. We also enable masking of zeros so that padding tokens are ignored during training, allowing the model to focus only on the real words in each sentence. The model uses an embedding layer to convert each word index in the input sequence into a dense vector of fixed size, called the embedding dimension. These vectors serve as numerical representations of the words. Because they capture semantic information, they allow the model to work with the meaning of the original text in a form it can process mathematically. To compute a masked average representation, we first expand the attention mask so it lines up with the embedded input sequences. We then multiply the embeddings by this expanded mask. This step sets the embeddings of padded tokens to 0, so they do not influence the result. As a result, only the meaningful, non-padded parts of the sequence contribute to the final averaged representation. We first sum the attention mask along the second axis to get the number of valid tokens in each sentence, which we will use to compute average embeddings. To avoid dividing by 0 when we later take this average, we then force this token count to be at least 1 by taking the maximum of the sum in 1. This simple safeguard ensures numerical stability during the averaging step. To build sentence-level representations, we first add together the token embeddings across the sequence, using the attention mask to ignore padded positions. This step gathers only the valid token information for each sentence. We then divide this sum by the number of non-padded tokens, so the result is an average of the valid embeddings. This averaging produces a consistent sentence representation that does not depend on the original sentence length. The final step is to print the sentence representations that have been computed. Each representation comes from the embedded token sequence for a sentence, adjusted using the attention mask, and then averaged into a single vector. This produces one concise numerical summary for each sentence. These vectors show how the model encodes and positions each sentence in the embedding space after processing. This script shows how to manage padding and attention masks in TensorFlow for variable length text inputs. It builds a small vocabulary from example sentences, encodes each sentence as word indices, and pads them to the same length, while creating masks that mark real tokens versus padding. These padded sequences and masks are turned into tensors and passed through an embedding layer to get dense vector representations. The script then computes a masked average of the embeddings, so that only real tokens contribute to the final sentence representation. Finally, it prints the padded inputs, masks, and sentence vectors to illustrate how padding and attention masks keep neural network models from being affected by extra padding values. Custom collate function. When moving from single text examples to mini batches, the default data loader behavior is not enough for sequence data, so you need a custom collate function. This function controls how individual samples are combined into a batch so that all sequences share a common length and alignment. It typically handles padding, sorting by length, and building attention masks, which are important for models such as sentiment classifiers. In practice, it turns reviews of different lengths into a single tensor of indices and labels, plus any extra tensors needed for efficient model processing. To design an effective collate function, focus on what the model needs at each training step. For each sample, gather the token index sequence and its label. Find the longest sequence in the batch and pad all shorter sequences to this length using a padding index. Stack the padded sequences into a two-dimensional tensor and the labels into a one-dimensional tensor. Also create metadata, such as attention masks, that mark real tokens versus padding, and tensors that store the original sequence lengths. For tasks like news topic classification, this collate function produces padded headlines, topic labels, valid token masks, and headline lengths, ready for the model to process. A custom collate function becomes important when your data pipeline is complex or specialized. It can combine multiple input fields, such as matching questions with answers or documents with summaries, and can also handle language-specific preprocessing and language identifiers in multilingual tasks. For applications like intent detection in chatbots, it can apply data augmentation while keeping batch shapes and labels consistent. By centralizing these operations in one well-designed collate function, you make debugging easier and allow the pipeline to adapt as the model changes. Python code, custom collate function. This script demonstrates a simple custom collate function that builds padded text batches from small toy sentences. It focuses on how sequences are padded and how the resulting batch shapes look, rather than on real data or complex logic. The goal is to help you understand the basic padding behavior when grouping variable-length text into a single batch. This script relies on PyTorch for working with tensors, which are multi-dimensional arrays commonly used in machine learning. It also mentions Torch Vision and Torch Audio as additional required libraries. The installation command is shown only as a comment, so it will not run automatically. Users are expected to make sure these libraries are installed in their environment before running the script. We begin by importing a module for generating random numbers, which lets us control randomness and make experiments reproducible by setting seeds. We also import the typing module, referred to with a shorter name, so we can add type hints to our code. These type hints clarify what kinds of data structures functions and classes expect. Together, these imports provide basic tools that support the rest of the script. We begin by importing PyTorch, which we use to work with tensors and perform data operations. We then import the dataset class from PyTorch utilities so we can define our own custom datasets. Finally, we bring in the data loader class, which loads data in manageable batches. Together, these tools let us handle large datasets efficiently during model training and evaluation. We start by setting fixed random seeds using both the random library and PyTorch, so that any random operations behave the same way every time the code runs. This makes experiments reproducible, because the sequence of random numbers will be identical across runs. As a result, we can more easily compare results, track down bugs, and ensure consistent behavior in our models and experiments. We use a small vocabulary as a dictionary that maps each word to a unique number. This dictionary also includes special tokens, where 0 represents padding and 1 represents unknown words. Common words such as I, love, PyTorch, NLP, is, and fun each get their own index. By converting words into these numerical indices, we can feed text data into machine learning models for processing. We define 2 special constant indices in the vocabulary to handle non-standard tokens. One index is reserved for the padding token, which is used to extend all sequences to the same length so they can be processed together in batches. The other index is reserved for the unknown token, which represents any word that does not appear in the vocabulary. Using these 2 constants allows the model to handle variable length sequences and unseen words in a consistent way. This function tokenizes a piece of text by breaking it into individual words. It first converts all characters to lowercase so that words like Python and Python are treated as the same token. Then it splits the text into a list of words based on spaces and other white space. This simple method is effective for basic tokenization tasks, especially with small datasets, or when the goal is to understand the general structure of the text, rather than handle complex language details. This function takes a list of tokens, which are words from a sentence, and turns each one into a numerical index using a predefined vocabulary dictionary. In this dictionary, every word is mapped to a unique integer. If a word is not found in the vocabulary, it is assigned a special index that represents an unknown token. The result is that a sequence of words is converted into a sequence of integers, which can then be used as input to machine learning models that require numerical data. In this example, we create a tiny data set directly in memory, where each item is a pair made of a sentence and a numeric label. The sentence is stored as a string, and the label is an integer. All labels are set to 1, meaning every sentence is treated as belonging to the same class. This simple setup is used to demonstrate how text data and their labels can be handled together in a basic text classification task. We create a class called toyTextDataset that extends the standard PyTorch dataset to manage text data paired with labels. Each item in this dataset is a sample made of a string and an integer, and all samples are stored together inside the class. This structure lets us organize the text and label pairs in a consistent way so they can be easily accessed, processed, and batched for later use in a model. This method defines how long the dataset is by returning the number of samples it contains. It does this by taking the length of the internal list of samples. Knowing this size is essential so that data loaders can determine how many items are available. This allows them to iterate properly over the dataset during processing your training. This method takes a specific sample from the dataset using its index, then extracts the text and its label. The text is split into individual words, and each word is converted into a numerical index using a predefined vocabulary. It then returns a dictionary where the list of token indices is stored under the key input IDs, and the label is stored as an integer under the key label. This format is designed so the data can be directly used as input to machine learning models. A custom collate function processes a batch by separating the inputs and labels from each item. It loops through the list of dictionaries in the batch, takes the token index sequences from each one, and stores them in an input list. At the same time, it extracts the corresponding label from each dictionary and stores it in a label list. This organization prepares the data for later steps, like padding and converting to tensors, so that all sequences in the batch have a consistent length. The code scans through all input sequences to find the one with the greatest length. It measures each sequence, tracks the longest, and records that maximum length. This value is then used to pad every sequence in a batch, so they all share the same size. As a result, the model receives inputs with uniform tensor shapes. We begin by creating two empty lists to prepare our data for a neural network. One list will store token sequences that have been padded, so they all share the same length. The other list will store attention masks, which are sequences of zeros and ones that mark which positions are real data and which are just padding. Together, these lists allow us to form uniform batches that the neural network can process efficiently. For each input sequence, we compare its length to the maximum length in the batch and add padding tokens at the end, so all sequences become the same length. We then build an attention mask that marks real tokens with ones and padding tokens with zeros, allowing the model to tell actual data from padding. Finally, we store the padded sequences and their masks in separate lists so they can be converted into tensors for model input. We convert the padded input sequences into a PyTorch tensor of long integers so they can be processed efficiently by the model. We do the same for the labels, creating another long integer tensor that matches the input data type. We also turn the attention masks into a long integer tensor, which tells the model which positions are real data and which are padding. This setup is essential for batch processing, where all sequences must have the same length and the model must correctly ignore padded positions. The first check makes sure the inputs and labels tensors have the same number of rows so that every input sequence has a matching label in the batch. The second check confirms that the inputs and masks tensors have the same shape, ensuring each input sequence has a corresponding attention mask. Together, these checks protect the consistency of the data and are especially important for correctly handling padded sequences in attention-based models. The function returns a dictionary with three main parts used to feed data into sequence models. It includes input identifiers, which are the padded input sequences stored as a tensor, and an attention mask tensor that marks which positions are real data and which are padding. It also provides a labels tensor that gives the target label for each input sequence. Together, these elements allow models to handle variable length sequences correctly by focusing only on the meaningful parts of the input. We create a toy text dataset object from the list of raw samples so it can manage our toy text data in a structured way. This dataset stores each sample's token indices and labels, making them easy to access. By initializing it with the raw samples, we prepare the data for later steps like batching and padding, which will be handled by the data loader. We set up a PyTorch data loader to handle our toy text dataset. The loader uses a batch size of 2, so each batch contains 2 samples. Shuffling is disabled, which means the data is read in the original dataset order. We also provide a custom collate function that controls how batches are formed by padding sequences so they all have the same length. This code outputs the version of the PyTorch library that is currently installed. Knowing the exact version helps you check compatibility with other tools and libraries. It is also useful for debugging because different PyTorch versions can change features or behavior. We obtain the next batch of data by advancing the data loader's iterator, which returns a group of samples that have already been processed and padded by our custom collate function. This batch is then stored in a variable often referred to as the first batch. At this point, it is fully prepared and ready for any further processing or analysis steps we want to perform. We inspect the shapes of the main tensors in the first batch to verify the data layout. First, we check the shape of the input ID tensor to see the dimensions after padding and batching. Then we look at the attention mask tensor, which should have the same shape as the input IDs and indicates which positions are real tokens and which are padding. Finally, we examine the label's tensor shape to confirm it has one label for each sequence in the batch, ensuring every input sequence is correctly paired with a target label. We print the tensor that holds the padded input IDs to see the input sequences after they have been padded to the same length. Padding is required so that all sequences in a batch have uniform length, which is necessary for efficient batch processing in neural networks. By examining this printed tensor, we can check the padded sequences and confirm that the padding has been applied correctly. The attention mask tensor shows which positions in the input sequence are real tokens and which are just padding. This distinction is important because the model should not treat padding as meaningful data. By using the attention mask, the model can focus its computations only on the actual input tokens and ignore the padded parts. This helps improve the accuracy and efficiency of the model's processing. This script shows how to use a custom collate function in PyTorch to batch text data with padding. It defines a small vocabulary and tokenizer, builds a toy dataset of sentences with labels, and then pads each batch of token sequences to the length of the longest one. The collate function also creates attention masks that mark real tokens versus padding. A data loader with batch size 2 uses this function, and the script prints the shapes and contents of the padded input IDs, attention masks, and labels for the first batch. This demonstrates how to prepare variable-length text for models that require fixed-size inputs. In this lecture, you learned to tokenize raw text into sequences of tokens suitable for neural models, build vocabularies, and map tokens to integer indices, handling unknown and padding tokens, and create PyTorch datasets and data loaders that yield padded text batches and labels. In the next lecture, Lecture B, we will go over text models.
Thank you for your attention. See you all in the next lecture.